Okay, here we go. So, I used to hit this, everybody used to hit this a lot more than you do now. It used to be a huge idea of calculus before graphing calculators. Now, with graphing calculators, it's not as big a deal. But the idea is called curve sketching and using your pre-calc and calc knowledge to get a good view of the graph. Let's start with the pre-calc idea. Say you're given an equation, you want to see what the graph looks like, but it's not something you're familiar with. Well, then you might start by saying, based on old type ideas, do you know what the shape is? For example, you might know a cube looks like this, or a parabola looks like that, or an exponential looks like that. You might have some previous knowledge about the shape. You might also have in your mind, if I were graphing something that I didn't have a graphing calculator for, the domain. What are the three restrictions on domain? Negative in a even root. True. Okay. What else? What else can you not have in math? Negative log of negative or 0. Okay. What else? There's one more. 0 in the denominator. Okay, now all three of those things then will restrict the domain and allow you to say, okay, well, I don't even have to graph here because those x's aren't even allowed. That will help you get a view of the graph. End behavior. How do you determine end behavior calculus-wise? The limit as x goes to infinity and negative infinity. Is it necessary that you look at both? Can they be different? They can, actually. You can have different horizontal asymptotes. So you probably should look at both. Symmetry. By symmetry, I'm specifically saying even functions such as, give me some even functions. X squared. What else? X to the fourth. Okay, give me a trig function. Sine is not even, no. Cosine. Cosine, etc. have symmetry where? If you think about all these, they are symmetric about the y-axis. Okay? That actually doubles your graphing ability. If you know the right side, then you'll know the left side. Likewise, odd functions, they have symmetry as well. What are some odd functions? X cubed, sine, tangent, has symmetry about the origin. About the origin. Can't have symmetry about the x-axis unless it's a non-function. Anything that has the same behavior above and below the x-axis must be violating the vertical line test. So there is symmetry about the x-axis, but those are non-functions. Okay? All right. Zeros and signs, you know. Zeros tell you x-intercepts, and signs tell you above or below the axis. Cool. All right. Now that's all pre-calculus knowledge of what graphs look like. Let's talk some calculus knowledge. What does the first derivative tell you about a graph? Increasing, decreasing slope, that's true. Horizontal tangents, sharp turns. Derivative tells you a lot. What about the second derivative tell you? What does it tell you? Concavity. Are the slopes increasing or decreasing? Inflection points also are indicated in the second derivative. All right. So then, let's talk about curve sketching. We've done this a little bit, but we're going to go a little more here. If I gave you a table of f prime, and I told you that f prime is positive on 0 to 4, what does that mean? The function is Increasing. If the derivative is 0 at 4, then the derivative or the curve must go flat. There's a horizontal tangent. If the derivative is negative, decreasing. If the derivative is undefined at 6, that might indicate a sharp turn or a discontinuity. Now they say though it's a continuous function, so it's not a discontinuity. It is a sharp turn. 6 to 7 increasing, sharp turn increasing. So if I were to draw this, let's go increasing up to from 0. Actually, I want you to draw 0, 4, 6, and 7 because those are the points they talk about. Yeah. That's terrible. You get the idea. From 0 to 4, it is increasing. I don't know if it's concave up or down. Let's just go increasing. Then it goes flat. Now it's going to decrease to a sharp turn. So let's go decrease to a sharp turn. Increasing to a sharp turn and then increasing. So how should I do that? Go up. Like, how about just like that? That's a corner. Do you agree that's a sharp turn? All right, something like that. What about example 2? This gives you F double kind of perspective. If F double is positive, what does that tell you about F? Concave up. 0 is no concavity for a second, and it might be reflection when there's a sign change. Then concave down, and then undefined could be a couple different things. It might be a sharp turn, because if the derivative doesn't exist, the second derivative probably also is not going to exist there. And then concave down. So let's go a sharp turn here. So, give that a little sketch on your own. See if you can figure out a way to draw this. There are many ways to draw this, by the way. It doesn't have to look like mine, as long as it satisfies the condition. This does. That's hard. Like that. That's better. I have a hard time drawing it this way. I don't know about you, but I got a kind of a Texans logo. So it's all right. Let's go on to then what these graphs would look like completely and exactly without just shape knowledge. All right. So let's start here. Do you know what the basic shape of this is? X to the 5th or 6th? 2 squared cubed is. So try again. 6th. Okay, and go back and review our exponent rules for these things. All right, it's x to the 6th. How are you multiply? It's x to the 6th, which means it should go up and up on the outsides, yeah? Could take a lot of turns, but who's to say how many? Who's to say how many? Well, you're to say how many. How do you tell how many turns? Calculus. That's how you're going to say how many turns. Calculus. All right, we'll get to that. Number of turns, we'll have to use the derivative for that. What about any domain restrictions here? Is there any x that doesn't work? No, that's fine. What about zeros? X equal 1. Okay, cool. Anything else? -1. All right. So we have, so far all we have is this kind of deal, and I know it's going to eventually go like that. All right. Now let's get into the calculus. What is the derivative? Squared 2x. Okay. This will have zeros at 0 and plus or minus 1. Do you agree? Okay. So in terms of the shape of this bad boy, what about the points less than -1? What kind of sign of the derivative do we get there? I agree, it's negative. At -1/2. It's flat there and negative. And then right of 0, positive, and right of 1. Positive. All right. So I have some flat spots and positive. Good deal. Let's go to the second derivative here. What about symmetry? I never did even or odd. Sorry. Is this even, odd, or neither? It is even. When you put in a negative x, you get the same as when you put in a positive x. That's the key criteria for even. And so, because the square will knock it out, do you agree? Or because overall it's x to the 6. So, because of that, it's even. So what kind of symmetry does it have? Same on either side of the y-axis, yeah? So there's symmetry on either side of the y-axis. That's good. I know some points. I've got some points. I've got some critical numbers. Now let's, should we do concavity? Let's start sketching and see if the concavity helps us. All right, so tell me, what's going to happen left of -1? So it needs to decrease till we get to the x-intercept at -1. At -1, what does the graph do? It goes flat. It's 0 and it crosses the axis and it temporarily goes flat. I probably should have started flattening out a little sooner here. Okay, so it's decreasing and it goes flat. Goes flat for a second. What does it do after? Decrease again. So it goes back to decreasing. And what is it? Just what is the y value at 0? -1. So it's going to decrease. Seems like it has a little inflection point in there. And then increase, flat, increase, yeah? I'd love to see if there's inflection points at the in between, but we'll call it good there. That's a pretty decent sketch. All right. Rather than do this one, let's go to the one on the homework. Last night you had one on the homework that you might not have been able to get started on. Let's give that a go. This actually is from CU exam from CU's calculus course. If you're going to CU, they have, at least the applied math division has a ton of old exams for you to practice and look at with keys and practice exams. A lot of good materials there. H is polynomial. Okay, so polynomial means x to some power, usually even powers, or not even powers, whole number powers. And it's odd. Okay, so what kind of symmetry? About the origin. H of 0 is 0. Cool. H of 1 is 2. They give us some points. They give us a whole lot of other stuff going on. I guess we're going to have to read all this. So these are just points, yeah? All right, so I can locate those in a second. They give us a limit. If it's a polynomial function, then you can bet it's continuous. So the limit, I'm sure, actually equals the point because of continuity. They give me a little left end behavior. This means as x goes to the left, the y values go up or down. Okay, and what about on the right-hand side? They go down, all right. First derivative test around -1 to 1. and they give you then some concavity action. All right then. Let's start talking about our graph here. That's the idea, is we're curve sketching. Seems like point-wise, if you just go to about -1 and 1 here, they also talk about a half, and so I'm going to do that in there. The y values seem to go up to about 2 that they give me, so that's my basic gist right now, right? So far so good? All right, tell me one thing you would do to get started. What's an easy, low-hanging fruit to get going with? The points. The points, 0, 0 is good. And 1, 2, 1, 2. Now, if it's odd, they actually gave you not 1 point, but 2. 1, 2 implies -1, -2. Symmetry about the origin. If it's odd, there should be symmetry about the origin, so you know -1, -2. All right. This kind of implies a point. Again, if it's continuous, then what x approaches the same as what it actually is? All right, so what point does that imply? When what? When x is -1/2, y is -1.5. This is 2. This is -2, so -1.5. Okay, that actually implies another point. What's another point? 1/2, 1.5. Again, because it's odd. So they've really given us 5 points to work with because of the odd. Okay. So if I look at these two things together, I have interesting points at -1 and 1 because of the first derivative, and -1/2 and 1/2 because of the second derivative. So let's break it up into all those different regions. What do you know about the region left of -1? Tell me 2 things you know. It's decreasing, and if it's concave, this is concave down on these regions, so it's probably, actually, do I know that? It doesn't, I wish they would have said only on. Let's assume it's only on. I think that is the assumption. So let's go with decreasing concave down. Oh, sorry, I didn't actually use the asymptote behavior here. What is it? Or not the asymptote. What is the end behavior here? What does it eventually do? It goes up here. So it needs to be decreasing and concave up here. Okay. And then what about from -1 to -1/2? Give me 2 things you know. Increasing by the first derivative and concave down on -1/2. Oops, that's -1/2. Yeah, sorry, it's concave up to -1/2. And then what about from -1/2 to 0? Increasing concave down. Okay, what about 0 to 1/2? Concave up and increasing. And it needs to have some kind of symmetry. And then what about from 1/2 to 1? Concave down, increasing. And then it starts to decrease. Is that symmetric about the origin? It is. Okay? It's difficult, yeah? Okay. That, if you have other questions on that homework, I'll come back to them. But now go to your one sheet of staples. This is your homework. I know it's kind of stapled. Don't sweat it. It's just a lot of spaces. It's really not that many problems. Okay? Well, you start with, so the problem is our textbook doesn't have a lot of AP type skills, so I need to supplement them. This is one. I had this on the test review, and I was planning to put it on the test, and I had good students coming in for help and said, I can't do this. And so I scrapped it from the test, but obviously we need to be able to do this. So the sub-lesson, I guess you could call it, is working from a table, which is a very important skill of calculus. Here we go. I'm going to go through an example of what exactly I want you to do, and the other homework problems are somewhat like it, some twist, but you should be able to think your way through it. This should get you started. All right, so in this case, I am giving you a table of different velocities at different times of something moving, all right? Our table time is in seconds and velocity is in meters per second. One of the most common things you need to do from a table, or be able to do from a table, is in question A. Estimate the acceleration at time equal 4. Now I'm given velocity. What's the big idea of calculus relationship to acceleration to velocity? Okay, so acceleration at an instant is the derivative. When they say not average acceleration over a time frame, but acceleration at one instant, then that is the derivative of velocity. So write yourself some notes here. Show the calculus idea. Don't just start going to the table and slapping numbers around. No. Okay. Please do write yourself these notes. These are meant to be notes to teach you how to do this well. Now, I cannot actually calculate the derivative. It is not possible because I don't have an equation with which to take the derivative or use all my derivative rules. The best I can do is go back to the foundational idea of derivatives, and that is, if you want the change at 4, remember way back when you first learned derivatives, you say find the change around 4 between 2 points, and then take the points closer and closer and closer together to approximate the change at 4, yeah? Now I can't actually get them too close again because I don't have an equation. But I can say that change between 2 points, average rate of change between 2 points close is a good estimate of instantaneous rate of change. Or if you like, secant slope approximates tangent slope. Write that down here, please. Use average rate of change or slope between 2 points to estimate instantaneous rate of change. Slope at a point. Now, this is important in terms of AP type grading. That squiggly equal is the star of the show. They will look exactly directly at that. And if you say equal, you're out. They will not even read it. You cannot find the derivative. If you think you are finding the derivative, you don't know what you're doing, you're done. Okay? It is an approximation. When you see this on the AP test, please underline that part, because that means they're looking for the hard equal. And if you say hard equal, like I said, you're done. All right, now, you're estimating this with change between 2 points. Next, always show the setup, not straight to the numbers. Here's what I mean. Don't just start pulling from the table. Communicate to the person, this is what I did, not make them look at it. They're using a 14 here. Where's that from? No, that's not their job. It's your job. So if I want to change at 4, I think you'll agree that's in here. So what 2 points would be logical to estimate change at 4? 3 and 5. Okay, now that's trying to stay true to the idea of a limit of getting as close as you can to the point of interest. That's really the limit. Could I use 0 and 9? No, that's too crazy. Why did you go that far when you could get close to the point by taking 3 and 5? So 0 and 9 is a no. Now, here's what I mean by always show setup. Do not just go 14 minus 8. Say, I am going to do change in velocity at 5 and 3 over change in time. Isn't that what acceleration is? Change in velocity over time. Okay? Show that then. That is crucial. I do not want to figure out where your table junk is coming from. I want you to communicate, this is what I'm doing. All right. V at 5. What is V at 5? 14. V at 3 is 8. In other words, the velocity increased by 6 meters per second in 2 seconds. So the acceleration is 3 meters per second per second.
So it's okay to get rid of this.
Good question. I was hoping you would say something like that. Now, what about this? You just said they were so picky about the equal sign. What are you doing? Well, in terms of this is a part of the concept here. These two are not equal. This is not the derivative, and that's why that is there. Now, these two, they're equal. This is that, and that's why that's a hard equal. Now, as far as the overall big picture, if you were to read this in all totality, this is what reigns the whole problem. The acceleration at 4 is approximately 3 meters per second. But as far as what's truly equal, these two truly equal. These two, approximation. These two, truly equal. These two, truly equal. Yeah? Okay. All right. So it's very common that you approximate a derivative from a table and you do it by average change between 2 points. Is that understood? First concept. Yes. Cool. It's also very common that you approximate an antiderivative or a definite integral by a table. You could do, there are at least 5 different estimation methods. There's left hand, right hand, midpoint, Simpson's rule, trapezoids. There's all these different ways to estimate an integral that we'll talk about, all of which we'll talk about this year. But right now, you know rectangles. Left hand, right hand, and midpoint. In this case, we're going to estimate the integral, but first, they're asking you to tell me, what does this mean? So conceptual, then numerical. What does it mean when you, yeah, it's the displacement. What if the velocity is always positive on the integral? If the velocity is always positive, then I'm always moving, let's just assume right, and I'm always moving right. So not only is my displacement 5 meters, but it's also my distance. Now, we'll talk more about that later, but in the case that you know for a fact velocity is always positive, then you have to say both displacement and distance. But because we have a table here, we don't really know. It seems like he's always moving right, or she's always moving right, or whatever is always moving right. You don't know. And so that would be a leap to say displacement and distance. In this case, we're just going to say displacement. So the integral represents the, all right. Now, would you count to 4, please? This, when they ask you to, not really, just count, hang on just a second. Yes, I'm sure you can count to 4. But, okay, when you do an integral interpretation, they look for 4 things. What it is with units, when it is with units. So they will say, all right, first of all, did they nail what it is? The integral represents displacement. Now, units. What are the units in displacement? Meters. In meters. Now they're looking for you to interpret the bounds. Do you know what those bounds mean? It's the displacement just forever? From time equal 0 with units. Seconds to time equal 9 seconds. 1, what it is. 2, units. 3, when it is. 4, units. What it is with units, when it is with units. They look for all 4 of those things. Understood? Okay. Now we're going to estimate. Ooh, there's that word again. Estimate. if you say 0 to 9 of v dt equals, you're out. Okay, you're estimating area under the curve with rectangles. You're not finding infinite area by actually integrating. You're estimating. It is an approximation. Right Riemann sum is fancy calculus code for rectangles. Now, if I were to talk about how many rectangles, I can tell you that starting out a picture's pretty handy. If you do enough of these, you'll start blowing off the picture. But let's do a picture, okay? So really quick, and I mean a rough picture. 0, 1, 2, 3, 5, 6, 9. And this is 8, 14, 19. Don't know what the curve looks like, don't really care. All right, now, if I'm doing rectangles, how many rectangles will I get? There'll be 3. Okay, now usually the question will say using 3 subdivisions as indicated by the table or something like that. I'll have to look it up. But the idea is you're using 3 rectangles. Each base is a delta x. I guess you could, or delta, not delta x, sorry, delta t. And each height, normally I'd say function, but in this case the function is v at some time, yeah? So the first, I didn't give myself enough idea. This is terrible. All right, so what's the first time frame? How many seconds in the first time frame? 0 to 3. Okay, so the first time frame is, now this, I'm not picky if you say 3 minus 0 or just 3. I'm fine either way. What I do care about is that you don't go straight to the table, like I said before, for the heights. Now, if I'm using a right Riemann sum, then in this first subinterval from 0 to 3, do I use the height at 0 or the height at 3? 3. Say v at 3 to communicate, hey, for my first height, I'm using the velocity at 3. Now, as far as the meaning of what that is, you're really saying, hey, you traveled about 3 seconds at a rate of 8 meters per second. So in that first time framing, I'm estimating you changed position by about 24 meters. The next time frame is how many seconds? 2. This time I'm just going to go to 2 seconds. If you want to show 5 minus 3, cool. I'm not picky about that. I am picky about showing how you found the height. V at 3 or 5? 5, which makes that 2 times what is V at 5? 14. That means in those 2 seconds you traveled about 28 meters. And then finally, okay, how many seconds in the last interval? 4. And what? V at 9. Okay, so that's 4 seconds at roughly 19 meters per second. That is 76 meters. 24, let's see, 24 and 76 is delightful. That's 100 plus the 28 is 128 meters. You change position by roughly 128 meters. You could also say at time 9, I was roughly 128 meters from where I started, something like that. Okay? If acceleration is greater than 0, is your estimate in B an over or an underestimate? What does acceleration greater than 0 imply about velocity? Velocity is increasing. If you have an increasing function and you use right rectangles, then am I not going to be using the biggest height in the subinterval? And in this, I'm going to use the biggest height in the subinterval. So if V is increasing, right rectangles will overestimate. You will say my estimate is over the true value because, please don't say because the rectangles are bigger than the curve. I understand, that's not math. Okay, because we used right rectangles on an increasing function. You follow me? All right. Last but not least, once in a while they'll throw you a bone and say, okay, I gave you the table, but now I'm actually giving you the equation. This is calculator active. The ones with stars you can use for that. Given the equation for velocity is this equation, and I'm giving you position at time equals 0 was 17, whatever that means. Find the position at time equal 9 seconds. How do I find position at time equal 9? I'll call it x at 9. I know that's weird starting out to see x as the dependent variable. But what's the independent variable? No. What's the independent variable? What does x depend on? Time. Where you are depends on what time. Yeah. Okay. So x depends on time. Okay. How do you find it? We have velocity. What's the velocity relationship to position? Derivative of, okay, so velocity is the derivative of position, or position is the antiderivative of velocity. You need to be able to go both ways, obviously. So in this case, because I have velocity, will I be taking a derivative or an antiderivative? Antiderivative, and I don't want to actually, this is calculator active, so I don't actually have to take the antiderivative by hand. I can do this with a definite integral. Question is, how do I do it?
17 plus the
Okay. So we talked last week a lot of integral is when you have a rate of change, you can find amount by taking start plus change, yeah? What's the starting position? 17. And how do you find the change in displacement, or change in position, which is also the displacement? How do I find the displacement, or change in position? Integral from 0 to 9. And so that's where the calculator comes in. If you take the starting position 17 plus the change in position, the integral, then you get something like, this is where you go to your calculator. All right, I'm slow, but I got it. What do you think? 120.6395. Okay, cool. What does that seem to indicate the displacement was? Is that all displacement? No. What does the displacement seem to be? 103-ish, yeah? Do you agree that displacement's about 103? Yes. Does that jive with what we already said? We said the displacement estimate is 128, but we knew that was an overestimate, so it seems reasonable, yeah? Yeah. Okay. That is what I want to see. The next 3 problems are then practice on tables. Hopefully it'll go well. And we'll go over tomorrow. Let's talk about questions on the homework. What questions do you have on set 61?
Number 1.
1. 25. 8. 125. didn't give you a problem number in box 2. You could have done 2, 3, or 4, yeah? You used it for 1.
Do 4.
You weasel. All right, just skip it. Or if you used it for box 1 because you needed the room, that's fine.
Answer is 27.
27? Okay. All right, number 1. Okay. 61, number 1. Let's go with... All right. Did you just make this a floating triangle, or did you put it on a coordinate plane? Floating? Okay. What did you, the hypotenuse is? 5. So did you use X and Y here, or B and H? B and H. Okay, cool. What are you trying to optimize? Area. Maximize or minimize? Maximize. All right. So the equation for that is obviously base height divided by 2. If you could get it down to 2 variables, that's your next objective. Can you use some other fact to sub? Yeah, Pythagorean theorem, base squared plus height squared is 25. I don't really care. It seems the same either way. Did you solve for H? Or B? Doesn't matter, whatever. It's 25 minus b squared square rooted is 1/2 b root 25 minus b squared for the area. Okay? Okay, so is that what you had?
Yeah.
All right, so that wasn't the problem then. Was the problem the calculus? All right, check your derivative. What is your derivative? Product rule. Chain and chain. 1/2 b. First stays the same, and the derivative of the second is? 1/2. That to the negative 1/2 times negative 2b. Okay? So first stayed the same, derivative of the second by chain rule, plus square root of 25 minus b squared, and then the derivative of the first is just 1/2, yeah? Okay, you want to know this is 0 or undefined? What would you do to get there? Get a common denominator, sounds good. The common denominator seems to be 2 root 25 minus b squared. What is the numerator here? If I divide out a 2, I get negative b squared, yeah? And this, you had the 2, so you just multiply the top and bottom by root 25 minus b squared, which gives you a normal 25 minus b squared. Is that what you had when you put it together? All right, now what do I do? Yeah, let's just go 25 minus 2b squared. So I'm going to just put them together. Okay, so a prime is equal 0 if b is? Plus or minus, but minus obviously doesn't make any sense, but plus or minus 25 over 2 square rooted, or 5 over root 2, in terms of max or min, I imagine before that it's probably pretty small here, so positive, and after that we're subtracting a larger, so negative. So did we get a max there? If the derivative went positive to negative? Yeah. Okay, so now answer the question. You should be on your way. I don't know if it says dimensions or maximum area or what's the greatest area, but you can get it from there. 25. Is 25 still a question? Anybody need 25 still? That was weird.
Yeah.
Okay, value of m so that y equals mx is tangent to the natural log curve. Now, first understand the question. Here's natural log, and you should focus on the fact that you have no y-intercept. There are lots of tangent curves, but as far as one that goes through the origin, that really can only be one line that has a tangent line. I'm just going to call that A for some magical point where the tangent line must be drawn so that the tangent line passes through the origin. You understand the question? Okay? Give me one thing you know. I can imagine gathering two facts. Give me something you know. What? Derivative. Yeah, the derivative. Doesn't the derivative at that point have to have a slope equal to the tangent line? So what is the derivative? The derivative at A equals m. So that means 1 over A is m. All right, that's cool, but obviously that's not enough. What else do you know about the two graphs? They have to meet. They have to touch at the point of tangency. So that means if they intersect, then isn't the line at point A MA? And that needs to equal the log at point A, which is natural log of A, yeah? Between those two things, then, you should be able to get going. If you substitute this in there, then you get 1 over A times A needs to equal natural log of A, which means 1 equals natural log of A, which means A is B. So, great, did we answer the question? They said find M so this happens. What is M then? 1 over A, which is 1 over E. So 1 over E is our answer. That was a hard one, to be sure. But that's a lot of higher level thinking, and that's only going to get better at by practicing. 8. Is 8 still a question? Okay. So start with F double at all points is 6. That's important because that means that I can integrate and get F prime, and it's easy to integrate. What's the antiderivative of 6? 6x, and I get a constant, right? Now, in order to get the constant, I need to know some kind of condition. They tell me that F prime at 1 is 4. Given F prime at 1 is 4, then I can say the derivative is 4 when x is 1, which tells me c is -2. So the function is 6x minus 2. The derivative is 6x minus 2. Now you can integrate again to find f. That should get you. Okay? All right. Have a great day, my friends. Have a great day. Yes. Let's go. Hi. Good. I don't. Sorry. Let's hear it. Come on, sing for me. Start spreading the news. Now you. Whoa. I feel like you should. If I'm going to sign this, you should.
I'm pretty sure no sound runs in here.
Oh, so terrible.
Or if you don't, then we'll just
No
buy
one's
you
gonna buy a Santa
relentlessly.
Cruz.
No, we'll like relentlessly buy Santa Cruz for you unless you help us with Santa Cruz.
Well, I would be happy to help, but my voice is terrible.
No, come on, just go talk to Mr. White. All the help.
Mr. White would have to give me a lot of help. He would have to be a genius. Yes, that's
He's good at what he does. I mean,
I hear it. Actually, he did a great job with my daughter, and she was terrible too.
he's made an actual player and a men's player. And that's an achievement.
Yeah, he does great work. I really like him. He's a good guy.